let's take a look at signed integers. Positive and negative. How do we go about representing that in memory? We have to think, wow, David, positive and negative binary numbers, how does that work? Well, what happens is the most significant bit, and now this is the bit to the furthest left, this is what we use to determine the sign. Okay, so the furthest to the left, 0 is for positive and 1 is for negative. And then the weight of each remaining bit is again the standard power of 2. Now, for negative, the weight is the negative of that corresponding power of 2. So to do this, what we do is we calculate and store using what's known as 2's complement. And how does this work? We're going to dive into it. Okay, so we need to always know how many bits the number is stored in. This is absolutely crucial, and it goes back a little bit to what we discussed earlier with that number of bits and what's the maximum size of the number that we can store in that so we don't get integer overflow. And this becomes really important because our most significant bit to the left is actually used for sign, not for the calculation. So when we're thinking of that, are there 8, okay, or 16, 32, or 64 bits? Really important. So 2's complement, what is this? To calculate our 2's complement, this is what we're going to do. Okay, we invert the bits using the bitwise NOT operation. That sounds all very technical and like, oh, that's deep, Dave. It's not that deep. We flip them, that's it. Okay, we add 1 to the resulting value. So whatever that result, when we flip them, we add 1 to it. Okay, let's have a look at this. 85 base 10, 8-bit positive binary number. There we go. 01010101. Straightforward. Now we're going to flip the bits. So you'll notice we've flipped the bits. What was a 0 becomes a 1. What was a 1 becomes a 0. We flipped the bits. Now we're going to add 1 to it. Okay? We add 1. Now when we add 1, 1 to 0, okay, is 1. 1, 0, 1. So you can see we've added 1 to it. And because of the way of the number, there's no real run through of changes, just that first one, 1, 0 plus 1 is 1, we bring it down. Okay, nice. So our negative binary number is 10101011. We've got now that stored, negative 85. 16 bits. Positive binary. It's the same, but we've now padded it out with zeros. We flip the bits. Oh, that's changed things a little bit. Now we're going to add 1. And you see what we get. So, as a negative binary number, we've now done that. So that's how 2's complement is working. Let's have another look, okay? 80 base 10, 8-bit positive binary number. There we go, we flip the bits. Now it's going to get really interesting when we add 1 to it, because we've added 1 to 1 and we get 0, carry the 1. Add 1, carry the 1. So you can see that run-on effect where we added, whoops, it wants to do that. I didn't want to go to 16-bit yet. So I added the 1. Okay, 1 plus 1 in this case is 0, and we carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 0, I'm at this one. 0 plus 1 is 1. 1 plus 0, 0, 1. There we go, because we finished off that carryover. And we go through with our 16-bit version of this. So you can see when it's 8-bit or 16-bit. You can imagine if it was 64-bit, okay, becomes larger in that sense. We flip them, we add 1, and here we have the number that we're looking for, 80, okay? I say 80 base 10, converted to binary, and then converted into a negative number. So that is binary 2's complement and the storing of negative binary numbers.